Congratulations, you won $200 billion and decided to start a space company to go to space, just like any good billionaire. So you build a rocket, send it straight up, and watch it fall down to Earth. You scratch your head as to why that happened, then shrug it off and decide to build a bigger one to stay in space. So you spend a few more $1,000,000, put it on the launch pad, and watch it fall down to Earth even harder. Well, shoot, this is going to be harder than it looks. The most fundamental piece of orbital mechanics is gravity. This is a force that acts on anything with mass. You, your rocket, the Earth, the Moon, your mother, and pulls them toward each other. It uses this equation, which looks complicated, but just means that as the mass of either object increases, or as the distance between them decreases, the force of gravity increases. Basic stuff. Technically, you're being pulled by a star that's several thousand light years away and much larger than the Sun, but it's so incredibly far away that the force is minuscule compared to the force from the Earth. So why does your rocket fall straight back to Earth every time you launch it? Gravity. But by this logic, you'll just keep falling down to Earth every time you launch and never stay in space, right? Well, not quite. When your rocket shuts off, it enters a state of freefall, not just going down, but at any point where the only force acting on it is gravity. If you apply a little horizontal motion to the rocket, it will land further away in that direction. If you get more and more horizontal velocity, you'll notice it takes longer and longer to fall because of the curvature of the planet. It has a longer distance to travel. If you get even more horizontal velocity, and we're talking like 17,000 miles per hour, you're going so far left that the planet has curved away from you and you just keep falling indefinitely. People call this missing the ground, although I don't really agree with this because if you miss the ground so much, why did you go up in the first place? Anyway, if you really want to stay in space, you won't be missing the ground so much as the atmosphere. If you don't, you'll put yourself in a decaying orbit where the air will reduce your horizontal velocity and you'll end up hitting the ground. Well, more like burning up into a pile of ash as you undergo the process of re-entry, but that's an explanation for another time. To avoid the atmosphere, you'll need to stay above the Kármán line, where space begins and defined by the Fédération Aéronautique Internationale as being Technically, it's at 100 kilometers above sea level, but air particles can be found for thousands of kilometers above it. So great job, you just sent a rocket up and then a whole lot to the left and now you're in an orbit. I mean, you could have just been more efficient to do a gravity turn, but like, yeah, it's your choice. What's a gravity turn? Oh, I'm so glad you asked. It's pretty simple actually. You sent your rocket up and then to the left, which works but isn't very efficient because you'd be losing the height you worked so hard to get while building that horizontal velocity. What most rockets do instead is go up while building horizontal velocity, thus being far more efficient. So now you're in orbit. Well, this sucks. I want to go higher into deep space. Well, you need to raise your orbit. You can just point your rocket away from the Earth and fire the engines, right? No. No, of course not. Obviously not. If you think that's true, you should feel bad and click off this video and go find somewhere else to prove you're a failure. Space is complicated, and whatever you think makes sense will do the opposite. If you want to get into a higher orbit, you need to point the spacecraft prograde and fire the engines. It's just like getting into orbit and then going a little further, or a lot further. Oh, look at that. You've entered a highly elliptical orbit, an orbit where the apogee is far from the perigee. It's just like a Molniya orbit, or a tundra orbit, or that thing that comets do when they decide to pass by once every year before being a Discord mod at the edge of the solar system. Okay, so a lot of jargon was just thrown out there. If that scares you, well, buckle up. It's time for the definition exhibition. We'll start simple. Perigee, or periapsis outside of Earth, is the lowest point of your orbit, the point that's closest to the planet. Apogee, or apoapsis, is the opposite, the furthest from the planet. If they're close, like this, you have a circular orbit. If they're far, you have again a highly elliptical orbit. It's characterized by this, but also having a high eccentricity and in many cases, high inclination. The term elliptical comes from the fact that the orbit is shaped like an ellipse. For those who didn't pay attention in 10th grade, so everyone, an ellipse is basically a circle. Some are round, some are squished. This is the center, this is the vertex, this is the covertex, throw it in Desmos, who cares. What we really need to know are the foci. Each focus is an equal distance from the center and lies on the major axis, a line that connects the vertices and also runs through the center. They have a lot of other special properties I could go into, but that would require math and that hurts my head. The distance between them can also be used to calculate eccentricity, find the vertices and covertices, and a bunch of other stuff, but again, just Desmos. The most important thing about the foci is that one focus represents the planet, in this case Earth, and the ellipse itself represents the orbital path. You starting to see how this works? It's not totally accurate though, because remember, the spacecraft is also pulling the Earth in a tiny itty bitty ellipse, so there's a bit of error in this model, among some other things. Moving away from my geometry rant, inclination. This is the angle between your orbit and the planet. But wait, the planet is a sphere. How can it have an angle? The Earth's axial tilt is 23.4 degrees off from the normal to its orbit. Even the Earth's orbit is inclined relative to the Sun, but the Sun doesn't have an equator, so the galaxy? I'm going to stop you right there before this becomes an existential crisis. Most astronomers and scientists use the equatorial plane as a reference. Everything in space is relative. There's no up or down, north or south, so it doesn't really matter. Just stick to the standardized system. Now, if you rewind a bit, you'll notice I said normal. Unlike you in middle school, this line here is normal. Normal to this other line. In physics, the term normal means perpendicular. So if you want to change the inclination of your orbit, point the spacecraft normal to your path and burn your engine. You'll go from this to this. Notice how the point where you burned is still in the same location. The opposite of this is called antinormal. For the sake of simplicity, we'll say normal is up and antinormal is down, and in spite of anything else you may have heard, there is absolutely an up and down in space. I also mentioned the word prograde. This is even easier. Forward. Face the direction you're going, burn your engine, and you'll go higher. The opposite is retrograde, backward. Face the opposite way, burn your engine, dip too steep into the atmosphere, burn up and explode and die. Or don't. Probably don't. The last thing I want to look at is radial out and radial in. Also pretty simple. In this case, radial in is pointing towards the Earth, while radial out is pointing away from the Earth. These are also perpendicular to your orbit, but in the same plane. Normal and antinormal are perpendicular to your orbital plane. For those who didn't pay attention in 9th grade, this is a plane, a two-dimensional area that goes to infinity in all directions. An orbital plane is just a plane on which your orbit lies. Inclination of the plane makes it a new plane with an angle relative to the equatorial plane. Pretty easy, you get it. So these help you determine the three dimensions in space. Can we move on now? Now say you want to land on the moon. Go ahead and burn prograde until your trajectory lines up with the orbit of the moon. Make sure as well that the moon will be close enough to pull you in once you reach this point. This is known as entering its sphere of influence. No, this isn't a reference to US bases being on every continent of the Earth. This is the threshold where the moon's gravity is stronger than the Earth's, due to you being closer to the moon. So now you're under the moon's gravity. Are you orbiting the moon? No, you're not. That would be simple, and nothing can ever be simple here. Your speed is currently greater than the escape velocity of the moon. You've entered a parabolic trajectory. What's a parabola? It's this. Basically, this means you're going almost as fast as an Arizona Ranger shooting outlaws in Agua Fria, and you go flying right past. That is, assuming you're not on course to hit the moon, because then, yeah. So, based on what you've learned so far, for those who are still somehow paying attention, what do you think you'll have to do to enter the moon's orbit? If you said burn retrograde until your apoapsis and periapsis are roughly the same distance, congratulations, you've earned a golden star. If you didn't, you've earned a free one-time use of the Alt and left arrow keys on your keyboard. Try it now. Anyway, you've entered into lunar orbit. To descend and actually land on the surface, burn retrograde until your apoapsis is below the surface. You're now on a suborbital trajectory. This is another type of parabolic orbit. Be sure to slow down once you get there, or else, yeah. I'm not going to go into much detail on that because it sort of goes outside the spectrum of orbital mechanics, and at this point, I can't be bothered. We can do that another time. In reality, there's a lot more we can go into, including geosynchronous orbits, interstellar mechanics, transfer windows, delta V, impulse, gravity assist, rendezvous, and 3 Library of Alexandria's worth of mathematical equations and formulas that would deplete your attention span faster than literally staring at a brick wall. If you want me to attempt to learn all that and explain it to you and probably fail in the process, go ahead and let me know. Otherwise, you've made it to the end. You now have a bunch of useless information in a field you probably don't do much in. But hey, I hope you learned something and had fun while doing so. Thank you for sticking around to this point, and as a reward, here's a picture of Iron Man. If you want to like and subscribe, go right ahead. I don't really care. Comments, especially feedback or video suggestions, would be greatly appreciated, as would any sharing of the video. Otherwise, I'll see you next time, and take it easy.